Hello, this is Dr. Strickland. In this video, we will investigate drawing and assessing the relative stabilities of resonance contributors. Take a minute to read through these student learning objectives. These are the things you should be able to do by the end of this video so that you're ready for the more difficult things we will do together in class. So last time we talked about the basic rules for how to draw resonance contributors, and these are examples of the kinds of things we'll see. We'll see that when a pair of pi electrons moves from a bond to an adjacent bond, it becomes a new pi bond. When a lone pair of electrons moves from an atom to an adjacent bond, it becomes a new pi bond. Or when a pi of electrons moves from a bond to an adjacent atom, it becomes a new pair of non-bonding electrons. And these are really the three kinds of electron movements that you're going to see. So let's just take a look at these one at a time. And, this is the kind of question that you might see. Draw the second resonance contributor and the resonance hybrid for each of the following compounds. So now the first thing that you have to do is identify whether you have any delocalized electrons in your molecule. So what I'm looking for is, first thing I look for is sp or sp2 atoms. So I've got a couple here, and then the question is, does one of these adjacent atoms have electrons that can move? Well, this is an sp3 atom, but it does have a pair of non-bonding electrons. So this is a delocalized system. It involves these three atoms. And with any delocalized system, the atoms will be contiguous. They're just kind of in a line, not necessarily a straight line, but in, touching each other. So I can see that I can move this here and that there. And so the second resonance contributor would look like this. So remember, none of the atoms move. So you can actually draw all of the atoms in even before you do the results of these electron movements. So this pair of non-bonding electrons moved to an adjacent bond and became a pi bond. This pair of pi electrons and that pi bond moved to the adjacent atom and became this third pair of non-bonding electrons right there. And the negative charge was on the carbon here, it's on the oxygen there. So still the same three atoms that we saw, as the delocalized system here. And so the resonance hybrid has to involve just those atoms also. Here's the methyl group. All this carbon is right in the same places. The hydrogen there. There's an oxygen here. We know that there were two pairs of non-bonding electrons that didn't go anywhere. You can put them kind of wherever. Okay, so where is the movement? Well, there was a change here between these two carbons, and there's a change here between the carbon and the oxygen. And since here we've got a negative charge on the carbon and here it's uncharged, we need a partial negative here. And the other place where we see charges coming up was with this oxygen, uncharged here, negative charge there, so a partial negative there. And so that's how I would do the second resonance contributor and the resonance hybrid. And in all of them, all of the changes have to do with the same three atoms. Okay, now this thing about the most stable resonance contributor we'll come back to because we need to get down to the bottom of the page and talk about that first. But let's do the resonance contributor, the second resonance contributor and the resonance hybrid for this one before we go there. All right, again, we're looking for the delocalized system. I see a couple of sp2 atoms. I see adjacent to one of them, there's an sp3, and it has non-bonding electrons on it. So that looks like a good candidate. So let's see. The second resonance contributor will involve all those atoms. Let's see. Now we know that electrons can't move towards an sp3 atom, but they can move away from an sp3 atom, which is what we saw up here, right? This is sp3 because it's got 4 electron clouds. It can start with an sp3 and move away from the sp3 towards an sp2. And that's what's happening here as well. One there and one here. And if you want, you can draw in the hydrogen, if that's helpful, because that's, of course, assumed there. And nothing else changes in the rest of the carbons of this ring, so I don't think I would draw those in. But let's see what happened here. Okay, so this pair of non-bonding electrons is still there. Here we have a pair of non-bonding electrons that moved to the adjacent bond and became a pi bond. Here we had a pair of pi electrons that moved to the adjacent atom and became a non-bonding pair. And if you calculate the formal charges, there's a plus here and there's a minus there. Okay, so in terms of resonance hybrid, what have we got? All right, so I'm going to put the atoms in. And the one pair of non-bonding electrons that doesn't go anywhere. I want you to draw the resonance hybrid. So pause the video, draw the resonance hybrid, including the partial charges, and come back. All right, welcome back. So the changes involve these 3 atoms. So these are the 3 atoms that will be involved in the resonance hybrid. So dashed line here and a dashed line here. And then as far as partial charges go, I've got no charge here and a plus there, so this is a partial plus. I've got no charge here and a minus there, so I've got a partial negative there. Okay? And I'm just going to highlight it to remind myself where the delocalized system is. All right, so let's take a look at how you assess relative stabilities, because the more stable a resonance contributor is, the more it contributes to the real structure of the compound. So here are some criteria that I go through, and I would do them in order. You know, a resonance contributor will be more stable when it has a complete octet on every atom that needs one, fewer or smaller charge separation. When there's a choice, a negative formal charge on the more electronegative atom or a positive formal charge on the less electronegative atom. And if there are carbocations, look for the more stable one. So these are the 4 things in order that I would use to assess the relative stabilities of a couple of resonance contributors. So come on back up here. You know, when it says a complete octet on every atom that needs one, the only atoms that don't need them are hydrogens, and then those group 3A atoms like aluminum and boron. But so hydrogen is the most common one that we'll see. All right, so here are our 2 resonance contributors. Let's see. This has an octet, that has an octet. I think all of these atoms have octets. And then when I check these, they all have octets too. Okay, so in terms of charge separation, we want to know, first of all, how many atoms have charges. So 1 atom in this resonance contributor, 1 in that one. So there's no change in either the size of the charges or the number of the charges. So charge separation has to do either with getting, you know, either a larger number of charged atoms or a larger charge on an atom. Neither of those are the case. All right, when there's a choice, a negative formal charge on the more electronegative atom. Okay, so negative charge on the carbon in this one and on the oxygen in this one. So since oxygen is the more stable, since oxygen is the more electronegative of these 2 atoms, this is the more stable resonance contributor, because oxygen, I'm going to say, has a higher electronegativity. You could say is more electronegative than carbon. And if you have an electronegativity table, you know, a stronger argument always has more information in it, so you could include the actual electronegativities for oxygen and carbon. I think that would be a great idea. All right, so when we come down to this second set, let's see what we've got. Well, again, we just go up to the top. Do all of these atoms involved in the delocalized system, do they all have octets? They do. What about charge separation? Well, this one has no charged atoms, and this has 2. So this one has something that makes it less stable. That makes this one more stable. And so because it has less charge separation, in this case, that means fewer charged atoms. Okay. All right, so come on down here to the bottom. Now, it turns out that molecules that have resonance contributors and resonance hybrids are more stable than they would be predicted to be. And the extra stability that can be experimentally measured, the extra stability that's gained from having delocalized electrons is called the delocalization energy. Okay, and here are 3 important things you need to know about delocalization energy and stability. So a resonance hybrid is more stable than any of its resonance contributors would be predicted to be. The greater the number of relatively stable resonance contributors, the greater the delocalization energy, and the more stable the molecule or ion will turn out to be experimentally. And then the more nearly equivalent the structures of these resonance contributors, the greater the delocalization energy and the more stable the molecular ion will be. And so this term equivalent means that they would have the same number and type of bonds and the same number of charged atoms with the same charges. All right, so that is the story on how to draw resonance contributors and assess their relative stabilities. If you have any questions, please bring them to me.